Hello all, myself Ragini, Assistant Professor from Department of ECE, Kamaraj College of Engineering and Technology, and today's topic of for the presentation is compensation techniques. And here comes to the compensation techniques. In electronics, in electronic circuits or in general electronics, biasing compensation is used to stabilize the operating points and improve the performance under varying conditions. So, varying conditions with respect to the change in collector current and base current, and as well as the VBE voltage across the base and emitter, we have to concentrate on the stability. So, whereas comes to the stability, the transistor has to be in an optimized point, so that we won't experience any instabilities and the underlying performances of the transistors. So, that we are concentrating on biasing techniques or biasing compensations, and after knowing that the stabilizing operating points should improve the performance of the transistors under varying conditions, as I said earlier. So, these are the types of compensation techniques I listed here, and the first one is thermistor compensation, where it comes to the thermal related compensations, thermal in the sense heat, and whereas transistor compensation is a type of a resistor, and it provides a compensation for to operate the transistor in a stability mode. And diode compensation, whereas the diode, one particular diode is inserted in the circuit, so that the diode will compensate the changes for varying conditions. So, coming to the transistor, here the transistor is a temperature sensitive resistor, and whose resistance will increases with temperatures, whereas the temperature increases, the transistor reflects that temperature changes or temperature variations across that particular part of the circuit. So, it is a positive temperature coefficient, whereas it mentions mentions the positive temperature coefficients alone, and meaning its resistance rises as the temperature goes up, whereas the temperature of that particular circuit or particular part improves or increases, it reflects on the transistor part. And here the thermistor is the second compensation method, whereas the thermistor is a thermal resistor. It is also a temperature sensitive resistor whose resistance varies significantly with the temperature. It is widely used in temperature sensing, compensation and controlling kind of applications. And this is the particular thermistor bias compensation circuit diagram, and this shows the diagram of transistor bias compensation. And in the thermistor bias compensation, thermal resistor has been inserted between the resistor R2 and RE, which is connected between the emitter, and here we have the components like R1 and resistor 1 and collector resistance RC, and here we have a VCC and voltage in here and voltage out. So, when the input gives here and the output is, we have to be in it has to be in stabilized conditions. This RT will take care of the temperature rises in this particular point, whereas the current flows here, we will ended up with some kind of a temperature variations, so that it will be compensated by using the RT thermal resistor. And coming to the transistor bias compensation, RS is inserted between R1 RC, and when the input current flows here, and the temperature variations across R1 and RC will be stabilized by using RC, which is nothing but the transistor bias compensation. And here I have given a flow chart kind of to understand the thermistor compensation, and when the temperature increases, the resistance of the thermistor decreases, and it is the property of NTC and negative temperature coefficient. And coming to the parallel combinations RT and RT, there will be an effective resistance that will decrease here, and the voltage at the base will also be decreased when we are inserting this RT, and voltage across base emitter will also decreases, and the current across the base also decreases, and collector current IC will also decreases. Biasing stabilization will be achieved here. So, when we decreases these parameters like IB, IC, VBE, VB and RT by decreasing the temperature, we will be achieving the bias stabilizations, and after that the emitter resistor and bypass capacitor further stabilizes the biasing property, and so that we can understand the thermistor compensation by using this flow. And coming to the transistor compensation, and here the temperature increases, the resistance of the transistor also increases, that is the positive temperature coefficient property, and the equivalent resistance of the parallel combination R1 parallel to RS also increases, and this increases reduces the voltage, base emitter voltage VBE decreases, and base current decreases, and collector current decreases because of the resistance of the transistor which is increased due to the temperature, and it is also decreases in IC compensates for the increase in IC due to the rise in IC naught, VBE and beta with the temperature. So, it also stabilizes the biasing property of that particular circuit, and this is the flow chart of the transistor compensation method. Diode compensation method is another compensation method used in all of the electronic circuits. So, here the diode compensation method against VBE variation, any kind of variations across the VBE will be compensated by using or inserting the diode into this particular emitter part, so that this diode should be of the material which cancels the effect. So, VDD is applied to the diode, it ensures a forward bias condition. So, the diode and transistor of the same material is been chosen, and the same electrical characteristics of the two particular diode gets cancelled each other, so that the temperature variations gets nullified. So, the VBE temperature coefficient is around 2.5 millivolt per degree Celsius, and the temperature variation across changes in VBE causes a small fluctuations as well, and the voltage at the diode VD also changes by the same amount, and the compensation effect happens here, whereas here in the particular diagram, and it changes the VD and VBE cancel each other. So, the stabilization is achieved by inserting this VD, and it will take care of the compensation, and it ensures the temperature compensation, which is a reliable performance despite of any kind of a temperature variations inside the circuit. So, these compensation techniques in any kind of electronic circuits can be implemented, and so that we can able to observe the stabilizations for irrespective of any temperature variations. So, this is the summary of this particular topic, and thank you for listening.